Welcome everyone. In this video we are going to talk about how to find the equivalent inductance of inductors in series and in parallel. So let's first start with the series case. So let's say series. And this is pretty straightforward actually, as you will see. So let's say that we have one inductor, L1, and another inductor, L2. Now, the question is, I want to replace these two guys by some inductance, which is going to, let's say it's going to have the value, I don't know, L equivalent. And I basically want to express this L equivalent in terms of these two inductances, okay? So, to have the same effect as these two guys, I want to just have one inductor. And what should this inductance be in terms of the given inductances? Okay? So what do we know for the... Alright, so if we have some current here that's coming from, rest of the circuit, let's say. And we know, obviously, I guess I should prove this, but let's say that we want to prove this in a future video, hopefully. But the voltage across an inductor is given by L times di by dt. So you have the inductance and then the time derivative of the current through the inductor. And you could put a minus here. I'm just interested in the magnitude of the voltage, okay? I guess it doesn't really make sense to say magnitude of the voltage because voltage is not a vector, right? We can only talk about the magnitude of the vector. So you basically just say the absolute value, okay? The size of the voltage, let's say. I think you get what I'm trying to say. Anyway, so that is given, let's say. Please accept this for this video and hopefully in a future video I can prove this. And so we basically want to express the voltage, right? So we basically have V1 plus V2. So that's like the voltage across the first guy and the voltage across the second guy. And this should equal the equivalent voltage. Because you're trying to mimic the behavior of the two inductors, right? And so what can we write? We can write then that we have L1 di1 by d2 plus L2 di2 by d2 equals, well, let's say L equivalent I guess you could say I equivalent over dt. Okay? Now, some things will simplify, don't worry about it. The thing is, we know that I1 and I2 are both I. Because the current through current through L1 and the current through L2 are the same, and we just call that current I. How do I know that? Well, because they are in series. That is, by definition, if two circuit elements are in series, that means the current through them is the same. So basically, we could just write di by dt plus, again, di by dt there. Okay? Equals L equivalent. And well, di equivalent by dt, that's also di by dt. Why is that? Well, because you have this, so you have the rest of the circuit that is providing this current I. And you're just replacing these two guys by the equivalent inductance. That doesn't change the current. That shouldn't change the current, because if it is changing the current, you aren't mimicking the behavior of these two guys by replacing it with this one inductance. You're changing something. You shouldn't be changing anything if you are to mimic the behavior of those two guys, right? The voltage didn't change, the total voltage didn't change from here to there, and the current also shouldn't change. That's the condition that we're working with. And obviously this simplifies. But I guess there is a complication, right? If di by dt is 0, but then again, if the current isn't changing at all, and then the voltage across them is 0 anyway, so it really doesn't matter whatever you put there. It's as if these guys aren't even there, right? So we don't really need to worry about simplifying by di by dt, okay? And you obviously see that then L equivalent is L1 plus L2. How would I memorize this? Well, you don't need to memorize it. It's pretty straightforward. You can just prove it. Or you could just say, oh, inductors add in series just like resistors. And it kind of makes sense because inductors are just just coils of wire, right? They're just wires at the end of the day. So it kind of makes sense that they would add like resistors, which are Again, kind of wires, I guess, but special wires with a high resistance. Anyways, to that series. And I guess you already have an idea for what parallel will be. It's probably going to be like resistors, right? And that is right. But we want to prove that. So for the parallel case, we're going to have... Oh, and by the way, I guess you could make the generalization, you know. What if you have three inductors where you would just add the other guy, right? You would basically... If you have n of them, you would basically do this. For each and every one of them, you would add as many as you have, okay? That's the way you would do that. And I guess this, how would you see it? Well, so the way you would see it is, you know, you found the equivalent of these two guys. And if you have had another guy, that will be just be in series with the LEQ equivalent that you already found, but nothing changed. So the same maths gives you the same addition way, basically. So that's that. And let's do the case for two inductors again. I mean, we don't really need to do it for two. We could do it for n, but like, I think it is pretty intuitive how to generalize it. That's why I'm not bothering to do it with n inductors. L1, L2, I1, I2. And I just want to replace this with L equivalent. We already discussed that this current is I. And this voltage is V. I'm going to make it a little faster now. So you have V1 like that, and you have V2 like that. Basically, V1 is equal to V2, which is equal to V. So with this being said, well, what is V1 then? Okay, so let's see. Well, V1 is going to be... So I'm writing V1, right? It's going to be, L1 di1 by dt, and then you have that equaling L2. Is this the way? You know what? Let's not do like that. That's not a good idea. So basically, what I want to do is, I know that the current is equal to I1 plus I2, right? Basically, the current comes in and it splits into two, so this is correct. And what is I? Well, I know that since V is equal to L equivalent di by dt, if I take the time derivative of both sides, I'm going to have that. And at this point, if I substitute for di by dt, it's going to be V over L equivalent equaling, well, so for the di1 by dt, it's going to be V1, right, over L1 plus V2 over L2. And as we discussed, these are the same. So you get that 1 over L equivalent is equal to 1 over L1 plus 1 over L2. This is the way you would add resistors in parallel, and it turns out it is also the same way of summing them for inductors, which again makes sense because inductors are just wires. And again, if you think about what if you had n of them, well, if you had n inductors, you would basically have, you know, you would have the I3 there, and then, you know, to IN. I didn't have to say that. Anyways, so up to IN, right? And then you would have the other guys there. Then I will erase this part, by the way, to not mess up the calculations, to not make it look messy. So you would have it like that, and all of them would just add like that. You would have 1 over L1 plus 1 over L2 plus 1 over L3, because all of the voltages are the same, right? If we were to have another inductor like that, the voltage across V3 would be the same as V1, and would be equal to V2, would be equal to V. So it's still the same way of adding them. So let me just erase that part so it's not looking confusing. And okay. Right. And what happened there? Anyways. So if there were n inductors in parallel, you would basically do 1 over equivalent inductance for those equals, you want to sum all of them up, like so. Okay? So this is it. I hope this video was helpful. If you have any questions, please write them in the comment section. I hope to see you in another video. Until then, take care.